Okay, good morning. So, sorry that we had to miss, what was it? Monday's lecture wasn't really up to me, but so let's see if we can manage to do two today. Okay, so first of all, I want to remind you, I'm going to go back to it also in the second part. Projects. So I missed one, this was, I guess, one office hours, but there will be office hours also Monday, Tuesday. So hopefully I'll get to see all of you. And basically that's it. So we're going to have the poster presentations, and then you'll have a few more days to finish the report. I wanted to remind you that there's going to be an exam also. Unfortunately, it's the last day of the exam period, but really there's nothing we can do. I mean, I'm not happy about it either, and the TAs are not, but that's what we got. So, and basically it's going to be just like the midterm, but we have a little bit more time. So there's 2 hours, closed book, cumulative, but only the stuff that we talked about in class. So I'm giving some examples here, and we're going to give you some practice exams. And one thing that I wanted to remind you, because people always ask questions about it. So basically, we're kind of separating between the exams and the homework, where the exams are mostly about machine learning, and the homework is mostly about the applied part of machine learning, as you already know. And we're going to keep that distinctions. Questions? Okay, so let's just remember where we are. How do we do this here? Let's see. Yeah, okay. So we're talking about Bayesian learning, and this is basically the scenario that we have in mind. We try to understand what is the probability of a hypothesis given the data. We use Bayes' rule, and we basically show that we can do this in the maximum likelihood case as the probability of the data given the hypothesis times the probability of the hypothesis divided by the probability of the data. So the scenario is that we have multiple hypotheses to consider. We know how to compute the 3 components on the right side, and we use this as a way to choose the hypothesis as the argmax over the set of hypotheses. So that's basically everything there is to know. We also looked at the case of uniform hypothesis, where really it's going to be called the maximum likelihood hypothesis, where we actually don't have any priors, and we basically choose the hypothesis that maximizes the observed data. So that's actually everything there is to know. The rest is applications of this, and we're going to apply it multiple ways. The first thing that we did last time is this example of choosing a coin. So we assume that we have a coin, and we have 2 possible hypotheses. Either it's a fair coin or it's a 60% bias in favor of head. And we show that by observing data, we did the case of 1 coin toss, we can actually distinguish these things. And then I also ask you, let's run over it, to try the case of many coin tosses. I think we said, let's assume that we have 100 coin tosses where you get 70 heads, and the computation is in the next slide. Basically standard discrete probability. So let's skip this. So the more interesting case is the more realistic case that we ended with last time, which is I have a coin. I don't know what is the bias. I know that it's a real number between 0 and 1, where P here denotes the probability of head, 1 minus p, the probability of tail. I toss the coin m times. I see k heads. What is p? And all of you said that your estimate for p is going to be what? K over m, which makes sense. But the question is why? And basically, I was trying to get from you an argument for why, and I think we agree that you all feel that this is the most likely value. So if I'm claiming that actually I think it's a quarter, you would be able to show that m over k over m, is a more likely value. And indeed, that's the case. So let's just do this math. So in this case, we have infinitely many hypotheses. We have to choose one of them. So we know that if p is the probability of head, the probability of the data that we've seen, that is k heads out of m tosses, is exactly this. The probability of d given p is p to the k, y minus p to the m minus k. And it's important, there was a question about this last time, and it's an important, so I don't need to think about how many options are there for k heads out of the m, because I actually observed it, right? So I have one sequence of observation. For this specific sequence of observations, the probability that this happens, given that p is the bias of the coin, is just p to the k, y minus p to the m minus k. It's easier to work with logs, so I'm going to take the log likelihood rather than this. The log of this is k log p plus m minus k log minus p. And what I want to do is I want to maximize it relative to p. So I'm going to differentiate relative to p. We get k over p minus m minus k over 1 minus p. And if I solve for p, I get that p is k over m. So basically, your intuition, we proved it mathematically. Two things to say here. One is we made an assumption. We made an assumption, and the assumption is that this is the binomial distribution. I could have assumed a different distribution, and you're going to see it in one of the homework questions. And the same set of observations, if the probabilistic model that we assume is different, will give rise to a different estimation for the most likely value of p. So it's really important that we work within a specific family of distributions. The other thing is what would have happened if you never saw a head? What would your estimation be then? Could be 0. Would it really be 0? Let's assume I tossed it 3 times and you never saw a head. Probably it will not be 0. You'll just say, well, okay, you only threw it 3 times, so it's okay to assume that even with maybe a fair coin, you never got tail. You never got head. So basically, this goes to the notion of smoothing the probabilities. If k is very small, m is very small, you want to be able to smooth it away from 0, because it's okay to assume that these things can happen, maybe low probability events. Once you toss it 1,000 times, maybe 0 is a little bit more believable. Even then, you will probably try to keep it away from 0. So this notion is called smoothing. We're going to talk about it in the case of a specific model later. But basically, the idea is to move away the probabilities from 0, because if you want to use it later on, if you use 0 probability, it means something that depends on it will never happen, and you want to be able to do a little bit better. So there are multiple ways to incorporate smoothing. We are going to do it just as an ad hoc thing, but in fact, you can get the idea of smoothing directly by changing the prior distributions. And actually, there is a slide that I've hidden that explains that for people that want to look at it. Okay, so I want to move to other models. So this is one case where we basically use Bayes' rule. We estimated, we learned something. We learned what is the bias of the coin. We want to learn more complex things. So in order to do it, I want first to introduce a few probability distribution. Two of them we already talked about, or at least one of them. We talked about the Bernoulli distribution. We have a random variable that takes two values, 0, 1, with probability p and 1 minus p. This is just the coin toss case. Binomial distribution, you can think about a sequence of Bernoulli trials. So think about tossing the coin k times, and the question that you want to ask yourself is, how many successes or how many heads did you get when you toss the coin, in this case, n times? So the probability that you see k successes is n choose k, p to the k, 1 minus p to the n minus k. So, and I assume you've all seen it before. Basically, you can think about if x is the binomial distribution with parameters n and p, and y is the Bernoulli with p, you can think about x as basically a sum of n y's. So that's one probability distribution that we want to carry with us. A second one is what is called the categorical distribution. So think about, in this case, rather than a coin toss, think about a dice. So a random variable takes k values, where the probability for the value I is pi, and the sum of the pi's is 1. Okay, so if you have a dice, you have k equals 6, and a fair die, pi is going to be a 6. So, and multinomial distribution is to categorical what binomial was to Bernoulli. So essentially, we're looking at sums of variables. Xi is going to be the number of times I was observed in n trials. So again, you toss the dice 10 times, and you want to know how many times did I get 1, how many times did I get 2, how many times did I get 6. And therefore, I have a vector of results with k values, so x1 up to xk. This is the number of times I get 1, the number of times I get 2, the number of times I get k. And we know that the sum of the pi's is 1. So the probability of observing this is p1 to the x1 up to pk to the xk, with the coefficient, the permutation coefficient, n factorials divided by the product of xi factorials. And again, we know that the sum of the pi's is 1, and we know that the sum of xi's is n. Right? I tossed it 10 times, so I made 10 observations. So these are two types of probability distribution we want to carry with us, because we want to be able to use it when we use Bayes' rule in some more interesting models. So here is an example of how we want to use, or how we can use Bayes' rule in a more interesting case. So the scenario that we have in mind is we have a collection of documents. We have only 3 words in our language, A, B, and C. That will make it simpler. All the documents will have exactly n words. So each one could be either A or B or C. And given a collection of documents, documents can be either good or bad, 1 or 0. Okay, so what is the learning problem here? One potential learning problem would be you observe a lot of documents, and eventually you want to be able to get a new document and determine whether it's good or bad. Okay, so this would be, now of course, given a document, predict whether it's good or bad. So the question is, how do we make this a learning problem? And in order to make this a learning problem, we have to have some parameters. So in the generative setting, so in the discriminative setting, you're basically doing it in the homework, or you're doing something like this in the homework. You see a lot of examples. You have non-parameterized models, and you try to learn the parameters of this model. In this case, since we're playing the generative case, we're going to assume a probability distribution. Not a specific one, but rather a family of probability distributions. In this case, we're going to assume multinomial distribution that I just introduced. We're going to look at data, and the data is going to allow us to estimate the parameters of this distribution. Now we know the distribution that generates the data. Given a new document, we can estimate whether it's good or bad. That's the game. So let's see how we do it in detail. So what does it mean that we generate data according to the multinomial distribution? First of all, we decide which document we're going to generate. Is it going to be a good document or a bad document? So we are going to do this with the probability Pyi be equal 1, which is eta. So eta is going to be the probability of whether a document is good or bad. Then, once we decided whether it's good or bad, we place words in the document with some probabilities. So AI, BI, and CI are going to be the number of times the words A, B, and C appear in document DI. That is, the sum of AI, BI, CI is N. And we're going to have different probabilities for AI, BI, CI for good documents and for bad documents, right? This is actually what characterizes the document. So I'm going to assume this. The probability of DI, observing the document DI, given that it's a good document, y equal 1, is going to be this. So the parameters that I'm going to use are alpha 1, beta 1, gamma 1. And this is my factorial coefficients here that I showed before, and factorial over AI factorial, BI factorial, CI factorial. So again, so with this notation, what I mean is that alpha 1 is the probability to see A in a good document. Beta 1 is the probability to see B in a good document, and so on. So in the same way, I can have the probability of observing the document DI in a bad document, where I'm using the parameters alpha 0, beta 0, gamma 0. So that's what we have now. We know that the sum of the AI, BI, CI is N, the number of words in the document, and the sum of the alpha 1 plus beta 1 plus gamma 1 is equal to alpha 0, beta 0, gamma 0, and they're 1. That's it. So now I have the complete model. And again, let's distinguish from the discriminative case, which is perhaps conceptually a little bit simpler. We make assumptions on how the data was generated, right? So we assume it's this multinomial distribution with 7 parameters in this case, right? So 1 for each word, alpha 1, 2, 0, 1, beta 0, 1, gamma 0, 1, and eta, which is the parameter at the root. Now we observe data. The data allows us to estimate the values of the parameters. Once we've done this, we're done. So the learning problem here is really to estimate the parameters. Now we have a specific, a concrete probability distribution, and we can make predictions using it. So in this case, we're going to be Bayesians about how to estimate the parameters. So let's do this. So again, this is the story that we had. And this is the classification problem. Given a document, determine if it's good or bad. That is P of Y given D. We're going to use Bayes' rule. P of D it's equal to P of D given Y, P of Y divided by P of D. And we need to know the parameters. So how do we compute the parameters? So let's compute here the probability or the likelihood of the data that we see. So we derive the most likely value of the parameters by maximizing the log likelihood of the data. So I'm writing here the log likelihood of the data. I'm assuming that documents that I observe are independent. So I can say that the probability of observing this collection of documents is the product over the probability of each one of the documents separately. So which I can write as the probability over I, P of D given Y, P of Y. And now we can write this down. So here I'm introducing some notation. So what is the probability of observing a document DI? It's the probability of observing it given that it's good, plus the probability of observing it given that it's bad. So now I don't know when I look at a document whether it's good or bad. So the way I'm going to denote it is what is written here. This is the probability that it's bad, and I'm raising to the power 1 minus yi, which basically means if the probability, if this document, if yi is 0, then I'm going to take this component of the product into account because the power here is going to be 1. And this is going to disappear because it's going to be something to the 0, which is 1. On the other hand, if yi is 1, which means it's a good document, I'm going to basically, what's written here is this probability, and this guy disappears, it becomes 1. So basically, at the same time, I've written the probability of the document, even though I do not know whether the value of y. The value of yi. So this is just a trick that we're going to see several times in this way. So now I have a way to write down the probability of observing the data, or the log likelihood, in fact, of observing the data. And I want to maximize it with respect to each one of the parameters. The alphas, the betas, and the gammas. So what I'm going to show here, so first of all, I'm going to write down the log, because it's much simpler when you write down the log of the probability. And it's written here. So the yi goes in front of this, and the 1 minus yi goes in front of this. And here you have basically weighted sum of the log of the parameters. And I have to differentiate relative to each one of the parameters. I'm going to do it here relative to eta, which is the one at the top that decides whether I'm generating a good document or a bad document, just because it's the simplest thing to do. So differentiating the log likelihood relative to eta, you can see here that basically everything disappears. All this part and this part disappears. All I'm going to get is yi over eta from here, minus 1 minus yi over 1 minus eta from here. If this is 0, it's very easy to isolate and get that this is eta. Make sense? So let's think about what does this mean. It's basically the sum over I, yi over m. If you think a little bit about it, should make sense. So what is yi over m? I didn't get it. What?
Sigma yi minus eta equal to 0.
Why is that? You're asking?
How is it 0? Can you explain?
So I want to maximize the derivative in order to find the value of eta that is an extremum point. The standard way that we are doing maximization. Right? So basically that's the derivative of the log likelihood relative to eta. Should have been here d eta, sorry. That's the derivative. If the derivative is 0, then the value of eta is this. Right? So how do I find a maximum of a function? I equate the derivative to 0 and I solve for it. Yeah.
Professor, what is the term C summation of logs?
What is the term?
C.
Oh, there is a constant here. That came from this number and from this number, which I don't carry with me. Right? It's some constant that depends on the number of words of each type that I've seen in the document. it really doesn't matter for maximizing this, right? You can see that, so just take the log of this expression. You will get AI log of alpha 1 plus BI log of beta 1 plus CI log of C1 plus some constant that comes from this product. Okay? And I don't really care about this constant because I'm going to differentiate and it will disappear. Okay, so let's just see again, what have we done? We wrote an expression for the probability of a document. We use this trick of putting the 1 minus yi and yi as a power here. We then took the log because we care about maximizing it. It's the same as maximizing the log probability, only that the algebra is easier. On the way to taking the log, I omitted the log of this because it's just a number, C prime, here that I know will disappear. And then we start differentiating relative to the relevant parameters. I have to do it 7 times because I have 7 parameters here, and I'm showing the simplest case. This should be D log likelihood to D eta. And that's what I get. I want to find what value of eta maximizes this log likelihood. So I'm equating this to 0, and I'm getting this. So the algebra is clear. Does this make sense to you? Why? Yeah, exactly. So it makes sense that eta is going to be, eta is the probability of being good. So it's just the sum over I, the number of documents that are good. Yi is 1 for good documents, 0 for bad documents. So this, okay, so I'm just giving some comments here, and the important thing is that this makes sense to you. I'm also highlighting this important trick of writing it with multiplicative yi's, because we're going to use this several times. Now, the same can be done for the other parameters. It's going to be a little bit harder because there are constraints, right? So you cannot just assume that these alpha 0, beta 0, gamma 0 are independent, because they are not. They sum to 1. So when you do this, for the other parameters, you have to think a little bit more and take the constraint into account. I think we're going to do this in one of the homeworks. But basically, it's the same kind of idea. Okay, so that's another example of how to be Bayesian with a slightly more complex model. I want to introduce another model that I will not solve completely, but would be good for you to understand what it means. And this is a hidden Markov model on HMM. So what is a hidden Markov model? So let's think about it in the following way. So we have data that consists of 5 characters, A, B, C, D, E, and we have states. B, in this case, I'm going to have 2 states, B and I. So we can think about it in the following example. So unlike the example that I show here in the slide, I'm going to give a slightly different example. Let's assume that you generate sentences. And when you generate a sentence, the way you generate the sentence, first of all, you generate the part of speech tag, whether it's going to be a noun or a verb or a determiner or an adjective. Once you've generated the part of speech tag, now you generate the word. So let's assume you start generating a sentence and you decide to, and with high probability, the first part of speech tag that you're going to generate is a determiner. Now you can decide whether it's going to be D or A, but it will probably not be table, because the probability of table being a determiner is very, very low. Once you've generated a determiner and the word that it produced, you move to the next state and you generate another part of speech tag. What could that be? This could be an adjective. This could be a noun. Let's assume it's an adjective. Once you know it's an adjective, you need to generate a word in this state. And this could be big or nice. It's unlikely that it will be teach, and so on. So basically, we generate states, and from each state, we generate an observation. So this is how it's going to look. So I have states. In this case, I have a state B and I. I generated a state with probability. So the initial probability were P of B, in this case, was 1 and P of I 0. Once I'm in B, I produce a word with probability P of X given B, and then I move to another state. What can I do? I can either move to another B state with probability 0.8, or I can move to the I state with probability 0.2. And the same thing, if I'm in I produce a word, P of X given I can then move to another state, which could either be I or could go back to B. That's what I have. Looking at it, so what are the probabilities that are involved in doing this? I have to have some initial probabilities, beginning of the sentence, P of B and P of I. I have transition probabilities. When I'm in a given state, what is the next state I'm going to move to? So it could be, in this case, because I have only two states, it's P of B moving to B and P of I moving to B. And the same thing, P of I moving to, so P of B moving to B, P of B moving to I, and P of I to B and to I. And the output probabilities. What words am I producing in each state? So given that I say that I have 5 characters, it could be P of A if I'm in B, 5 probabilities, P of A when I'm in B, P of B, P of C up to P of E when I'm in B, and the same thing when I'm in I. So essentially, you think about this generation process, right? It's a sequential process where you start in a state, you produce something, you move to another state, you produce something, and so on. And there's a lot of things you can model with this process. The example that I gave was a part-of-speech tagging. A lot of sequential processes in natural language can be produced this way. The example that I show in the slide is the problem of chunking sentences to phrases. So imagine that you have a sentence, and you care about named entities, location, organization, and people in a sentence. And the way you're going to do it is each word, you will either denote it, in this case, okay, in order to do it, I need 3 things, not only B and I need B, I, and O. So each word will be either the beginning of a phrase, inside a phrase, or outside a phrase. And once you are in a state, you determine which word belongs to the state. You can also think about, being in one of 2 rooms, observing X in the room, and then either moving to the next room or staying in this room. So there are many processes that you can do with this. And then again, the question is going to be, I'm going to give you data, and you want to be able to estimate these parameters that I'm showing here. This is a family of parameters, 3 kinds of parameters that you have to estimate. The initial probabilities, the state transition probabilities, and the output probabilities. Once you know how to estimate this, you're done, and you can kind of estimate the likelihood of sequences or make predictions on these sequences. Now, why is it called hidden Markov model? It's hidden because typically we will not tell you, we will not know the states we're in. As in the example of the sentence that I gave at the beginning, I actually don't typically give you the part-of-speech tag. I just show you the words in the sentence. That's what you observe. However, it's useful to imagine that there is a state the part-of-speech tagging state or the BI state when you try to estimate the probabilities. So here is the abstract problem. We have data. The data consists of an observation. Each data item, 1 to n, consists of m observations and potentially of m states, maybe not. Maybe you don't observe this part. And you want to find the most likely parameters of the model. What are the parameters of the model? So these are what I call the emission probabilities, the probability of x given that you are in state. It's the probability on this arrow here from B to A. The transition probability, the probability that you're going to move to state Si plus 1 when you are in state Si, and the initial probabilities. So given an unlabeled examples, an observation, a sentence, x1 up to xm, we want to be able to use Bayes' rule in order to find the most likely label that could be the states. And again, we're going to use Bayes' rule in order to do it. So the way I'm presenting the problem here, it's actually a difficult computational problem. Because if the label is this, and let's assume that each state is only binary, there are way too many labels, right? 2 to the m labels. It's going to be a difficult computational problem. So there are good algorithms to solve this, which we're not going to talk about. But basically, it's the same game, right? So you want to be able to estimate hidden label. In this case, the label is a sequence from an observation. Questions? Yeah.
So do we know how many hidden states in this model?
Yeah. We know how many. We don't know what they are.
And the result is when we have the observation of each output status, and we predict which is the hidden status behind it, right?
Yes. So let's take the part-of-speech tagging example. So you know how many different part-of-speech tags are there: noun, adjective, verb, determiner, and so on. You see a sentence, and you want to predict the part-of-speech tag, the states. That's the problem. That's the computational problem. The way we are doing it is we are imagining that the way the data was generated is using this hidden Markov model. So first of all, the part-of-speech tagging was generated, given that a word was generated. And then we moved to the part-of-speech tag of the next word. When we were there, a word was generated, and so on. So we imagine that this is how the sentence was generated. And once you have a sentence, you want to figure out what were the states. What are the part-of-speech tags that correspond to this sentence? Answers your question?
Yeah. So in this, we know the sequence of A, C, D, A, D, and we know the output probability, like 0.5, and we don't know the transition probability, but we know how many hidden status. So we want to.
We don't know any of the probabilities. Everything has to be estimated.
Oh, so all the probabilities here are unknown.
Yes.
We only know how many hidden status behind it.
Right. We know the size of the vocabulary, and we know the size of the number of states. Right. So just like here. So in this case, at the top row, I know that the size of the vocabulary is 5, and the size of the states is 2. That's what I know. I don't know what is the initial probabilities. I don't know what are the transition probabilities to move from B to I, from I to B, or to stay in B or to stay in I. And I don't know what are the emission probabilities, which is the probability of producing A or B or C or D or E, given that I'm in B or given that I'm in I. So these are the three types of probability distribution: initial, state transitions, output probabilities that I need to estimate.
Okay, one last question. After predicting, we can only say that maybe for the first data, the B has the highest probability. We cannot say it must be B. The header status must be B, right?
So we see a lot of data, right? So let's assume that the data that we see, it's not hidden. It's actually, everything is observed. Let's assume that you see data this way. These are the observations. These are the labels, right? These are the states. Once you have the data this way, you can estimate the initial probabilities for each state, right? Because basically, I show you this, right? So you can estimate. You've seen 100 examples like this. You know that in 49 of these, I started with B, and in 51, I started with I, so you know what is P of B and P of I, initial probabilities. You look at all the transitions that you've seen in these sequences, and for example, if it's a binomial distribution, you can just do counting, and you'll estimate what is the probability to, if you are in state B, to transition to state B, if you're in state B, to transition to state I, and so on. So if you observe these complete observations, you can basically estimate all these parameters. Okay? The difficulty, and this is why it's called hidden Markov model, is in realistic cases, it will be an unsupervised problem. I will not show you the S's. I will just show you the X's. And you'll have to do something more sophisticated, basically learn in the presence of missing labels, which we're going to get to later today, in order to do the estimation. That's why I'm not talking about the estimation, just about the model. But if everything is observed, you know how to do it now, right? You can just look at all these examples and just estimate these three types of probabilities. Yeah?
Does HMM allow any state to be non-emissive?
You can invent another character that says emit nothing, so it will be okay. Okay, so again, the reason I'm mentioning it is we're not solving it now because, as I said, in realistic cases, it's a hidden Markov model, and I don't show you the states. I just show you the observations. But I want you to see that it's the same language that we're talking about, and we can basically play with it and do all the estimation just like we do for other models. Okay. So let's move on, and I want to move to an important component of this chapter, which is Bayesian classifiers. So when we start to talk about Bayesian classifiers, first of all, we want to think about it, about what are we doing here, right? So we talked about it as H being a collection of hypotheses, and we're being Bayesian about choosing the hypothesis. Now, in fact, H can be many things. We already saw example. It could be a class of functions. It could be a collection of parameters. It could be a collection of predictions. And you can be Bayesian with respect to each one of them. The issue is that what you're being Bayesian with respect to actually could make a difference. And let's look at this simple example here. So we are aiming toward getting a classifier, which is going to be the maximum posteriori classifier, this argmax over this. And we can think about it in two ways. So let's take this example to illustrate this. So let's assume that we have a space of 3 hypotheses, H1, H2, H3, and I'm giving you here the probabilities for each one of the hypotheses given the data. Given these numbers, you're going to choose H1. On the other hand, and given this selection, if I give you a new instance, and you know what the prediction is for each one of the hypotheses on this instance, given that you already committed to choose H1, you're going to predict 1, because H1 says that X has to be predicted to 1. So basically, that's going to be our prediction. On the other hand, so that's one way of doing it. On the other hand, if we want to directly predict the most probable classification, we don't necessarily have to commit to the hypothesis ahead of time. We can just keep the probabilities with us and then combine the prediction of all these hypotheses weighted by their posterior probabilities. So basically, you can think about it as deferring the commitment. What's going to happen in this case? So the way we're going to make the predictions is, just a second. Did I skip something? Okay. So the way we're going to make the prediction is this. The probability of V given D is going to be the sum of the probability of Vj given that we want to use the HI hypothesis and the data times the probability of HI given D, which basically means I'm not choosing a hypothesis, but rather I'm weighing the hypothesis. Now, one thing that I have to point out here that hopefully you've noticed is that P of Vj given H and D, I can write as P of Vj given Hi, because I've already chosen the hypothesis. The data doesn't matter anymore. So, and this is going to be called a Bayesian optimal classification. So I've not committed before. I'm basically weighing my decisions, kind of keeping everything until the last minute, and weighing, taking into account all the hypotheses and their predictions. In the case of the hypothesis that I showed before, the probability of me predicting 1, rather than it's being what the most likely hypothesis says, is weighing all these hypotheses. So it's the probability of saying 1 given that I'm using Hi times the probability of using Hi, sum over all the Hi. So in this case, it's going to be, then if you remember, the probability of the HIs were 0.4, 0.3, 0.3. Let's just go back to it. Yeah, so the probability of the hypothesis were 0.4, 0.3, 0.3 at the top line. And their predictions were 1, 0, and 0 on X. So if we remember that, so the probabilities were 0.4, 0.3, 0.3, and the predictions were 1, 0, and 0. So the probability of predicting 1 is going to be only 0.4, while the probability of predicting 0 is going to be 0.6. So because I did not commit to the HI, but rather maintain everything all the way, I did make a different prediction. I don't know if it's better or not, but it's something that basically now what I did is I was Bayesian with respect to the prediction rather than with respect to the space of hypothesis. And this is something that is called Bayes optimal classifier. And we're going to move in this direction and use one of the key examples of this is a very practical learning algorithm that is called the naive Bayes algorithm. So what do we want to do? So we're back to making predictions. So we are imagining that there is some function from x to v, finite set of values, and we want to make predictions, choose one of these v's, given an observation x. So Bayes' rule is going to tell us, okay, if you want to do the maximum posteriori v, do argmax over all v's, the probability of vi given x. We're using Bayes' rule, which means that we're going to look at P of x given Vj times P of Vj divided by the probability of the data. Because we are taking argmax, we can eliminate the denominator here, and we're basically just taking argmax over this. So far, very simple. Again, I'm using here a notation that, again, I'm sure you've seen before. I don't always carry with me P of y equal y, P of uppercase y equal lowercase y. I'm just calling it P of y. Okay, so that's the Bayesian classifier. Now the question is, how do we use it? How many parameters do we have to estimate here? We need to estimate P of v. We need to estimate P of the data given v. What is the problem that you will encounter here? So P of v means look at the 100 examples that you've seen. Let's assume v takes two values, v equal 1 or v equal 0. In the simplest case, just count how many of the examples that you've seen had v equal 1 and how many of them had v equal 0. That's P of v. What about this? What is P of x1 up to xn given v? Yeah?
It's the product of P of x size given v, because we're dealing with Bayesian assumption. So we'll be just assuming that the xi's are independent.
Okay, so far I've not made any observation and not make any assumptions. So what does it mean to estimate P of x1 up to xn given v? It's the data item that you have, and you want to know what is the probability of observing this data item given that v is 0, and what is the probability of observing this data item given that v is 1. That's what's written here, right? What is the problem with this? Let's assume n is 50 dimensions for the data. How many data items are there? Boolean variables. How many possible vectors are there if n is 50 and these variables are Boolean? 2 to the 50. So most of these probabilities are going to be 0. You've never seen this data, right? So that's, as is not a useful way to think about predictions, right? Because you don't know what are the probabilities of each data item given v. In order to move forward, we have to make some assumptions. So, as I said, estimating P of v is easy, but we cannot estimate the probability of the data given v. We really have to make some assumptions. And what kind of assumptions we're going to make really will dictate what kind of classifier we have. So then, and we're going to see several types of assumptions today and next week. Today we're going to make the strongest assumption that we can make, just so that we'll be able to do something. So let's start just by decomposing this probability distribution. So I'm basically just rewriting this. So far, so what is the probability? The probability of x1 up to xn given vj. I can always write it as P P of x1 given the rest of the xi and vj times P of the probability of the rest given vj, right? So that requires no assumption, right? And then I can keep on going, right? So I wrote the first line. Now, basically, I'm copying this. This is P of x1. I copied it here. And I keep on factoring this one. So now I'm writing P of x2 given the rest and Vj times P of the rest. And I can keep on doing it. So what I have here is the product of P of x1 given the rest, P of x2 given the rest, and so on. So far, no assumptions, right? That's something that I can always do. But still, I don't know how to estimate this because most of these are going to be zero given that I've only observed a small number of examples. So here is the assumption that I'm going to make. I'm going to make assumption that the feature values, the xi's, are independent given the target value, given the v's. What does that mean? It means that P of x1 given all the other xi's and v is equal to P of x1 given v, because it's independent of all the other xi's. And the same thing for each one here. P of x2 given the other xi's and v is just P of x2 given v, and so on. So I can write this as the product P of xi given v. Now, this last step is a strong assumption. It's an assumption that the xi's are independent given that you know the label. And this is the naive Bayes assumption that we're going to take with us. So what does that mean now, that we make these assumptions? It means that in order to estimate what we want to do here, in order to make prediction relative to using the VMAP, given that the feature values are independent given the target values, all I need to do is I need to estimate a smaller number of parameters. As before, I need to estimate P of V. And in addition, I need to estimate these numbers, P of xk given Vj. Now, if I have n feature values, that means that I have to estimate, let's say that V takes two values. I have to estimate 2n numbers here and a number here. So, which is a small number of parameters, and hopefully tractable. So let's summarize. So what is the learning method here? The learning is estimating the parameters. I have to estimate size of V plus n times size of V parameters, use them to make the prediction. We already talked about how to estimate. We're going to assume, for example, binomial distribution, just like the coin tosses that we had before, and we're going to use this, and we're going to learn parameters. Now notice that this is slightly different learning than what we talked about before, and we're going to kind of see the connection a little bit later, but we learn here without any search. We just look at data, we use this to compute some parameters, and that's it. And we have a way to make predictions. We don't even know whether we are consistent or not. Right? So we got a bunch of data. We use this to compute the parameters. These parameters are going to help us make predictions, but we haven't verified that we are making predictions in a way that is consistent with the data, which was the driving force of what we've done earlier. And again, the question of why does it work is going to be very important, and we're going to talk about it. So let's first make a couple of comments. So one is the assumption. So the assumption that we made is that the feature values are conditionally independent given the target value. So in the next couple of slides that I'm not going to go over in details, but you should go over it yourself, is I'm showing examples that the condition of conditional independence, which you're assuming here, and the condition of independence are different conditions. It's not that one is more general than the other. There are just two distinct conditions that share the word independent in them. So you can be independent, two variables can be independent, but not conditionally independent on a third variable. And two variables can be conditionally independent given something, but not independent. And the next two slides just show examples for that. I will not go over it, but if you haven't seen it before, just go over it yourself. What I'd like to do instead is I'd like to give an example. So now that we define what is the naive Bayes classifier, let's learn the naive Bayes classifier. And you've seen this data before. We used it for decision trees. Now we're going to use the same data to learn the naive Bayes classifier, which is the stuff that is written at the top right here. So again, we have 14 examples. We have 4 features, 1 label, binary label, and we want to be able to use the naive Bayes classifier. So before we had another algorithm. What are we going to do here? So here we want to estimate the probabilities. The first thing we want to estimate is the probability of the observation given V, which, as we said, we decomposed it to a bunch of simpler probabilities to estimate. So at the top, we want to estimate the probability of V, which is the probability of the label being yes, the label being no. And then this should have been structured a little bit better. But anyhow, what you see here is the probability of attribute, outlook, taking one of 3 values, sunny, overcast, rainy, given that play tennis, the label is yes, no. So there are 6 numbers here, right? How many numbers do we actually have to estimate if we want to know these 6 numbers?
4.
Why 4?
You know the probability of S given yes and OC given yes, you can estimate R given yes.
Right, so given that, let's assume that I'm given yes now. I have 3 numbers that I have to estimate given yes, but they sum to 1, right? So 2 of them are sufficient. And the same thing given no, the 3 numbers that I have to estimate given no sum to 1, so I need to estimate 2 of them, and I know the third one. And the same thing applies for each one of the other rows. But basically, what I will have at the end, not independent numbers, but numbers, I'll have 6 and 6 and 4 and 4, plus 2 here. And again, it's sufficient for me at the top row to estimate 1 number, and the second one is 1 minus it. So that's what I have to do, and that's going to give me the way to predict. So given a new instance, for example, this one, outlook is sunny, temperature is cool, humidity is high, wind is strong, I can make the prediction. How do I make the prediction? So this is the example. I already estimated that the probability of yes is 9 over 14, the probability of no is 5 over 14. And now in 2 columns, I'm writing here the probabilities that that I care about, given that this is my instance, right? So there are more probabilities that I estimate, but I don't care about them in this case. So here I care about, on the yes column, I care about outlook being sunny, temperature being cool, humidity being high, wind being strong, and the same thing given the no. So given that I'm in the yes column, the product of all these numbers is what I care about, right? So this is evaluating this where Vj is yes, And then on this column, I'm doing the evaluation of this product given that it's no. And I'm telling you that the probability of yes is, I'm using this sign here, proportional to this, which is the product. Why do I write proportional and not equal?
Because there's a term of P of data.
Right, so I don't care about the denominator, right? So I'm writing here, this is as an argmax. So I omitted the denominator. So it's really not the probability, it's just proportional to probability. If I really want to know the probability, I can normalize relative to this. But this is sufficient to tell me that probably the answer here should be no. The prediction here should be no. Okay, so that's what I'm choosing. And as I said, I can also normalize if I want to know the probability. That's it. That's the naive base. Now, a question that you want to ask yourself is, what if we were asked about outlook equal overcast? Let's go back to the data. Remember, outlook being overcast. Where is it? What do you see about outlook being overcast?
Always yes.
It's always yes. So the probability was going to be 1, which means, so what is the problem with that?
So the term in the second row first, your outlook equals overcast given no, that would be 0, and it'll make all of that 0.
Right, so if I have 1, 0 in one of these five numbers here, it means that I will never predict it. It will be 0. And this is exactly the issue of smoothing. So when we estimate probabilities, we typically estimate it this way. We use the binomial assumptions. So the probability of xi given 1, equal 1, given v, is the number of observations given the number of labeled examples, ni over n. But we can suffer from sparsity. If n is too small, maybe the estimation for ni is not believable. If ni is 0 or 1, it will dominate the estimate, and we will never predict v if one of the elements in this column is 0. So we have to do something. And what we're going to do is smoothing, which I mentioned before, and now I'm going to suggest a way to do this in the context of naive Bayes. Now, there are many, many ways to do smoothing. In the context of naive Bayes, it really doesn't matter how you do the smoothing. You have to do it, but the simplest way actually works. In more complex models, it does matter how you do the smoothing. But basically, in the context of naive Bayes, what we're going to do is we're going to make sure that we move the probabilities away from 0. So the way we're going to estimate the probability of xk given v is, instead of just nk over n, we're going to add something to the denominator, add something to the numerator, and make sure that, therefore, we never have 0 in the numerator. So I'm going to give you now the specific case that we care about here. So it's called the Laplace rule. For the Boolean case, m, the number of labels, is 2, p, the base probability is 1/2. So what we're going to get is, instead of nk over n, nk plus 1 over n plus 2. Very simple way to move things out of 0. And the interesting thing, if you sum over the xi's, you will see that you will get the sum 1. So basically, what was done here was done correctly in the sense that you maintain this being a probability distribution. Okay, in fact, I'm going to skip this. Okay. And stop here. So that's the end of what's today? Wednesday, Monday's lecture. And we're going to take a break, take some questions when we. Let's take the question when we meet again, and move on to a few other things that have to do with Bayesian stuff. So we'll meet again at 10:30.
Yeah, so basically we were just talking about it and we're kind of
So you
struggling.
were the number 12?
Yeah.
That's okay. Yeah, I responded to you.
Yeah. We're kind of struggling to find a direction from like the work we've done so far. And we don't want to go another whole week without making much progress, so we would love to make this possibility.
Except for now.
Okay. So I guess we'll just then try.
So
We'll go to
what is
Tina's
that?
office hours.
What is the course about?
So we're doing, we also have one other team who's coming at 10:30, who couldn't make it to this. We're trying to do something with hate speech detection on Twitter. And the feedback we got from the CAs basically was that this is a very well-researched area, which we also realized.
That's not the problem.
Right, but we're struggling to find like sort of a novel approach. We don't want to, as like it said on the website, we don't want to do an experimental approach where we're just like taking a data set and applying it to a classifier that's been done before.
Which data do you use?
We found a few different ones online that we were hoping to maybe combine and like clean and formalize.
And when you say hate speech, what exactly do you want?
That's one of the main issues we feel that we've learned is that the definition varies based on, different perspectives. Like, I don't know, we've just seen that as like a common issue from like a sociological perspective of this space. But I think we would probably just base it on like what the databases have already labeled and try to like synthesize like.
But all the data is going to be tweeted
That's the plan.
over what time period?
The different data sets we have are actually, I think, over different time periods. We haven't looked that much into the data sets themselves because we were afraid to go too far and then have to like totally pivot based on what the
So
CA
first of
said.
all, I mean, it's a great problem.
Yeah.
So the only issue is that you're right. It's a little bit boring if all you do is you take a data set and
Right.
classify. But given that you're taking multiple, for example, multiple time periods, even that is interesting because is it the case that if you learn something from, I don't know, 2015, it's going to work now?
Right.
Or
And we can
change.
maybe analyze like how the data has changed over the years and if hate speech itself has taken on different forms, like based on what our model
Right, so
learns.
that's already an interesting question, right? To see whether you can adapt. You can train in one time period and you see how it performs there, and then try to see how it performs in another time. Maybe you can even split it otherwise, and not only based on time. That's why I asked about sources. But it also depends how you got the data from Twitter. Specific hashtags or
Some of the papers we read, there's one paper that talks specifically about like a Twitter API that you can use to actually extract tweets and also extract metadata, so like who tweeted it, how many retweets, like the time of day it was tweeted, things like that. So we're thinking of on top, like we found like just labeled and annotated tweets online in data sets, but I was thinking maybe we could also apply some of these other like APIs on top of it to get out some metadata.
You can register with Twitter or something like this, and then you can get data based on different hashtags and some other criteria, and this will allow you to collect more data. So definitely don't stop. So work on cleaning the data, and we can talk next week. You'll be smarter next week. So, but I think there's a lot of slices you can do here in the city.
Okay, cool.
So if there's a lot of literature that we found in the space and just like finding that like based on what we read.
Yeah, so there is a lot of
I think the time period is a good idea. Seeing
yes,
like how
so
classifier does on
that
one
would be
data.
one thing, and you know, once you start playing with the data, maybe there's a few other ideas.
And one other thing we found, like in some of the papers we read, was the challenge of like one type, like maybe targeting language that's racist versus targeting language that's homophobic, and seeing if like the model is able to generalize over all different types of hate speech versus like targeting one specific kind. So that was like another thing we were maybe looking at that we could analyze.
Yeah, so I think there are many questions there, and even though there's been a lot of papers, I don't think this problem is close to being
Right.
addressed in interesting ways.
Okay, cool. Thank you.
We'll see you next week.
Yeah.
The denominator maybe should have been the number of values in the feature set.
One, but you can try the math.
So suppose you just looking at the probabilities of NIs given yes. Your numerator will have a summation of number of times there one plus you have the number of features. So you added one in the numerator and you added the number of classes in the denominator, right?
No, two. Yes, number of classes.
Right. So when you add all of these for all the features, the numerator will be added with add a value of number of features, while the denominator will only have the number of classes. So it won't exactly be.
Well, try to do it. I'm pretty sure it does. But I have to think about it.
For the TF-IDF stuff. So obviously, if there's already appears in the vocab, it never appears in the documents because it provides a zero error.
Yeah.
And so Yes.